Thank you, Ken. So model building to support exploration undercover. So what I'll be talking about is the construction of explicit models to characterize the cover. So in those areas where it's reasonable to do so, where the cover is actually has an interface at its base, even if it covers many layers, the geometry of that cover and the physical properties within it may be characterized through inversion. So I will acknowledge Glenn and Peter, who are both in the audience, for doing, as it says there, 100% of the work. Maybe they can answer 100% of the questions. But they have no idea how I shuffled the deck of their own slides, so I'll proceed with the presentation. Again, what we are talking about is explicitly modeling cover, and the great thing is now we have the techniques, the inversion techniques, to do it for many kinds of geophysical methods. And in putting together this, I actually thought about a summer job I had more than 30 years ago when I was a college student, and it was in Calgary, and I spent the entire summer doing exactly this, explicitly modeling cover for processing seismic reflection data. So I worked for Chevron that summer, and they had myself and a couple of other students doing exactly that. We were using refraction, so seismic refraction, to model the near surface as a number of layers with physical properties, velocity. And then those static models, as they called them, were used to apply what they called static corrections to the reflection seismic data. So for them at that time, over 30 years ago, it was absolutely essential to explicitly model the cover, understand the geometry of the base of the cover, of the layers within it, and the physical properties within it, in order to apply a correction so that they could properly see through that cover and correctly process their seismic data. So we know that with our geophysical methods in the minerals game, not seismic predominantly, cover often has a hugely negative effect on the data. Sometimes it's the primary control of the data. What we have within the data, though, is often the means to explicitly characterize that cover in such a way that its effect on the data can be understood through modeling, and then to at least some extent, we're able to see through that cover by, if I use the seismic example, correcting the data. So in other words, understanding this fuzzy filter that's at the top of the Earth, that's in some ways ruining or at least negatively impacting our data, to characterize that filter and fix it so we can see more clearly through. Of course, it's never the same. I mean, it's great to have perfect eyesight, but if you have to wear glasses, you get the right lens and you try and fix. You try and fix it to the best you can. So we have inversion technologies now that give us the capability of characterizing the cover. Obviously, inversion is still non-unique, but in many cases we have the geological constraints at the cover through drill holes, through edges of outcrop, to fix the cover at certain points or along certain lines or in certain places, and use those constraints to solve, to a great extent, the non-uniqueness problem and directly, explicitly model the cover. So in the work that we've been doing, or really Peter and Glenn have been doing, they've been using VPMG, which gives a proper geological model parameterization for the inversion. So you see the different modes there on the left, heterogeneous unit inversion, where you can solve for heterogeneity of physical properties within a given layer. Now just imagine that layer, though, is the cover, and the top is the topography. Geometry inversion, where you can fix the physical properties within the units and solve for the geometry. So if you can fix the topography and you have some understanding of the physical properties of the cover, you can then solve directly for the base of the cover. And then a homogeneous unit inversion, which we often use at the beginning of the process, where if you have some understanding in terms of a starting model of what the geometry may be, you can try to solve for at least an average physical property. So the inversion proceeds just as shown. It's multi-layers. In this case, for cover, it's at the surface. Drill hole constraints can be used, Pears point constraints as shown, or if a hole ends within a layer, that can be used as a limiting constraint as well. So I'll just go through a couple of case study examples using gravity and airborne EM. The first two are gravity. So this is the Boulia gravity inversion case study, sedimentary cover, Queensland, and the task was to construct the basement unconformity such that it's consistent with the gravity data. So there's the area, free air gravity data. First attempt, solving directly for the geometry of the base of the cover, assuming that the cover itself is homogeneous. So this is using just a simple starting model of an assumed constant depth and letting the inversion iterate until it finds the base of the cover under that assumption. So in this case, of course, what you see is that the base of the cover closely reflects the gravity data itself. However, if you incorporate some constraints, and I guess for us, when we talk about constrained inversion, that subject came up this morning, we mean geological constraints as opposed to mathematical constraints. In this case, we had constraints of various sorts. We had some understanding of physical properties. There were a couple of drill holes that actually pierced through the cover, and there were numerous water wells that didn't pierce the cover but provided a limiting constraint on where the cover depth could be. And there was also some magnetic depth to source solutions that gave us at least some help with a starting model. So using those constraints, you get a different model, a much more sophisticated one. So obviously, again, the inversion is non-unique, but by applying these constraints, and you can see the water wells are the kind of holes here, which apply a limiting constraint, so the surface can't go up through the bottom of those. And then there's actual drill holes that pierce that surface that provide an actual pierce point constraint to pin the geometry down. And I guess what we find is that it doesn't take, generally speaking, a lot of constraints to provide a lot of control. So minimal constraints can provide a lot of control on the resulting model, and you can get a pretty reasonable idea of what that cover must be, both geometrically and in terms of its physical properties. So the image at the bottom compares the initial inversion without constraints, just directly inverting for geometry, assuming a homogeneous cover. And that's the one where, you know, the form of that surface really closely reflects the gravity. So basement highs coincident with gravity highs. But then just a few constraints, such as this drill hole pierce point here, really change the form of the entire structure. So again, few constraints can provide an enormous amount of beneficial control on the inversion. My second example, also gravity. So this is the Maladina property. This is at the west, sort of near the western end of the Iberian Pyrite Belt. There's a basin with tertiary infill over the Paleozoics. And what we're looking at here is the gravity data. And there was outcrop on both the east and the west. And the idea here is this is very prospective ground through the basin, and the cover's not that thick. Nevis Corvo is just somewhere over about here. And there's other deposits in Portugal on the west side as well. So the understanding was that the primary control on the gravity data was in fact the overburden thickness and its variation, and the secondary control was the basement density. The idea here was to try to reveal something of the gravity data underneath that variable cover in order to generate targets beneath the tertiary fill. This is the topography, and essentially to the west of this line here and to the east of this line here, we have outcrops, so very good control on the bedrock surface here and here. The basin itself is within here. There were drill hole pierce points, so a fair amount of drilling had already been done within the basin. This is, I don't have a scale on here, it's around 30 kilometers from east to west across there. So here you see the various drill hole pierce points, and what that is doing is it's pinning down the surface where each of those spheres are. And here you can see the actual topography, so much shorter wavelengths there. So a smooth surface fit through the drill hole pierce points at the top of the bedrock. And the idea here was to apply the same style of inversion, to invert the gravity data to update that top of bedrock surface. So you get that. So I just go back and forth. See, the gravity inversion has really applied the same sort of wavelengths in structure, the top of the bedrock, as we have where the control is at the topography. Okay. So again, explicitly solving for the geometry of the cover. And once that cover is solved for in terms of its geometry, which you see on the left, so these white spheres are the control points, so it's sort of all control points where there's outcrop on the eastern and western margins of the basin, and numerous control points within the basin. What we have on the right here now is apparent density. So it's an apparent density inversion, which is really giving us a strong indication of where the actual gravity highs are underneath that cover. Okay? So this was actually a revolutionary processing there, and it directly generated new high-density targets by explicitly solving for and, in effect, removing the effect of the cover. On to a couple of airborne EM case studies where really exactly the same approach has been followed. In this case, a spectrum case study. This is one that Glenn presented during the conference. You can see the trace of the buried paleo channels within the original data. And here we're applying the same style of inversion to the airborne EM as we did just in the previous gravity example. So I don't know if that shows that well in the picture, but this is a three-dimensional surface, and if you can see it, these are cuts so into that surface. So these are elevation lows or the paleo channels. Right? The cover thickness itself is shown on the scale. So where the cover is deep, it's red. Where the cover is shallow, it's blue. But this is a fairly detailed and very explicit geometric model of the base of the cover solved for directly by inverting that data. This is another example that Glenn showed during the meeting, Tempest survey. Exactly the same strategy as with the two gravity case studies and with the spectrum case study. Okay. So in this case, the first approach was to adopt a two-layer model. As it says, the starting model cover thickness of 50 meters, so that's the red cover there. And then a cover conductivity was assumed, and then the model was submitted to the inversion to get an updated basement geometry, which you see there. And then finally, using that basement geometry, solving for heterogeneous conductivity within both the basement and the bedrock. Right? So an explicit inversion that preserves the geometry directly. Okay, but there were drill hole pierce points there that weren't used in that initial passive inversion, and they're shown here. See them? And those pierce points at the base of cover, you can see, are not coincident with the base of cover from the inversion. It's shown in more detail here. So the idea then was, well, let's have a second pass of the inversion. Now we have a real constraint, the drill hole pierce points. So let's constrain that surface to those pierce points. So that's done here. Right. So now you see the You see the base of cover here passing directly through the drill hole pierce points. So that's nice, but you also see that you're getting this conductivity heterogeneity here, which is a reduction in conductivity compared to what it is laterally on either side. So that was an indication that the conductivity was probably overestimated in the initial starting model, right, which is represented here. So another attempt was made, another pass of the inversion, and of course it's an iterative interpretive approach, as always, in which case the starting model conductivity within the cover was lowered to more clearly reflect what was shown here, where the actual drill hole pierce point constraints were. And by lowering the conductivity starting model, you get another pass of the inversion, you get a different structure. So it's a deeper structure here, but now we're consistent completely with the drill hole pierce points. And in solving for that heterogeneity within that geometry, also showing us some layering within the cover. So by following this iterative interpretive approach to inverting for the cover geometry and the physical properties within that cover, we're getting a model back that's geologically reasonable. It's respecting what we understand to be a fairly hard interface at the base of the cover, and it's explicitly respecting all the drill hole pierce points that we have. So in conclusion, a lot of the cover issues that we have can be solved by inversion when the inversion is geologically parameterized, so that we're able to explicitly solve for interfaces and then solve for heterogeneity within the units. Okay? And by doing so, I think there's a lot of areas. I know certainly in Canada there are a lot of areas that have really suffered in an exploration sense for what's actually relatively thin cover. I think this kind of inversion approach really offers a new way to not only characterize that cover, but in characterizing it, to apply other geophysical methods to, in effect, correct, for lack of a better word, the effect of that heterogeneous cover and give us a new view into the subsurface. And I guess I just have a few acknowledgements for the data itself. And that concludes my talk.
You're the sort of guy we love. You finish early. Any questions for John? All right.
Thanks, John. I just wanted to get some idea about what you think how these sorts of methods scale, because what I've alluded to before is the curse of the Voxette. When you go to try and use this sort of stuff on a broader context, you run out of puff pretty quickly. I just wanted to get some idea how would you tackle that problem?
Well, I'm not sure exactly what you mean. The inversion isn't done explicitly using a Voxette.
No, but the discretization in
right.
little, not necessarily exact same size cubes, but the fact that you're using a 3D discretization limits the scale, so the resolution scale problem.
The discretization done here is using the vertical prism discretization. That's what the VP is. So the actual number of model parameters is much smaller than with a true 3D Voxette, because here we can completely control the vertical discretization level. So for example, within the basement, if that's not the area of primary interest when we're trying to solve for the cover, I mean, at its limit, you only need one cell beneath the cover. Right?
Yeah, so you could degenerate back to a 2D grid almost for the whole of Australia. I was thinking how you're going to do that. How does this method scale when you want to do it?
It's still in 3D. It's not 2D. It's just that the parameterization is completely such that you control the number of cells vertically within each column, right? So compared to a detailed 3D voxet, the number of model cells is you know, it could be an order of magnitude or more lower, right? So.
Okay, I mean, we don't have to go 3 rounds on it now.
Okay.
All right.